So section 8.2 has to do with rotational dynamics, which dynamics are forces, okay, when we deal with Newton's laws. Force is telling us why things move, okay, why something is moving forward because a force has been applied to it, things like that. Torque is telling us how effectively we can cause a rotation based on our force, okay? So based on the amount of force we apply, what's the most effective position to apply that force in order to cause the most rotation, okay? So as you increase your radius, as you get farther and farther and farther apart from your axis, okay, or your point of rotation, your torque increases. Okay, so as you get farther away from the point you're rotating, the force you apply becomes more effective. Okay? So it's a little lowercase t. That's what that Greek letter is. Force times radius times sine theta. Okay?
That's force?
So the force you apply dependent upon how far apart it is from that axis. Okay, or your point of rotation.
You can't use like Newton anymore for that?
You'll use Newton for that.
That's why that's the force constant.
Variable.
You can also use that.
All right, so here's what torque kind of looks like, okay? If you apply a force, that's how much torque is being exerted. If you move it closer to the center, to the point of rotation, you have less force, okay? So kind of watch what's happening here. This person's exerting a force on the end of the wrench. As they move the force closer, you're going to get less torque, okay, because your radius decreases. So take a look at that equation we just got. If your R value goes down, what's going to happen to your torque value? It's going to go down, okay? Because if everything else stays the same, the angle at which you apply it, the force you apply stays the same. If you increase your radius, your torque will increase. If you decrease your radius, your torque will decrease, okay? So the closer you get to that rotation point, the harder it is for you. The more force you have to apply in order to get that same amount of torque, okay? All right, so let's go ahead and look at just an example here. This is our equation again. Theta is the angle between the force and the radius. Okay, so here we're applying a force straight down on this wrench. The radius is from the point of axis to wherever you're applying that force. Okay, so this red line is our radius. It's from the point of our rotation or from our axes to our force. So here, this angle between force and radius is a 90-degree angle. Okay, so theta would equal 90 in this case. All right, and as we apply that force down, the torque's going to end up going in the clockwise direction. Okay. So if I apply a force of 100 newtons to the wrench at a position 0.2 meters from the axis point, what's the torque? Okay, so find that torque. If I apply a force of 100 newtons to the wrench at a position 0.2 meters away, what's my torque? And we already established that our theta angle here was what? 90. Okay, so if I apply a 100 Newton force at a radius of 0.2 meters, and I need to take sine of 90. What's sine of 90 degrees? Okay, so sine of 90 just equals 1. So I'm going to take 0.2 times 100, and I'm going to get t equals what? 20. Okay. And our units are Newton meters. So Newton times meters. Most of the time they put a little dot in between the two. Newton meters. 20 Newton meters. Let's go ahead and turn to page 202. I want you to look at example problem number 1 on page 202. So go ahead and get your book out. We're going to look through this example problem number 1. Okay. L is what we call the lever arm. It's the perpendicular distance from the axis point to where the force is exerted. So if it says to solve for the lever arm, it's this term right here, r sine theta. Okay. And really, r sine theta we can plug into our torque equation, which it would just say torque equals F times L, if you wanted to do it that way. Anyway, if it asks you to solve for lever arm, you're just going to solve for the term r sine theta. Okay, and remember, theta is the angle between the radius and the force that's being applied. Okay, so between the radius and the force that's being applied.
So is that the lever arm equation?
Uh-huh.
Okay.
Uh-huh.
But you said you can also add it to the torque one too?
Yeah, if you wanted to just substitute this term, okay, r sine theta is in the torque equation. So F r sine theta, you could just substitute this term right here and take F times L. I won't write it like that, but that's essentially what you're doing. Okay? Does that make sense? Okay. So let's go ahead and start looking at this example problem number 1. We have this wrench that's applied, that has a force applied at a 60-degree angle. We know the amount of torque that we have to have in order to tighten this bolt. So it tells us that the torque we have is equal, it needs to be equal to 35 Newton meters. It says we have a 25 centimeter long wrench. Our radius needs to be in centimeters or meters? Meters, okay, because torque right here has to be in meters. So we need to convert that, so it's 0.25 meters. And we have a 60-degree angle. So if we redraw this wrench, which I'm a fantastic artist, so you'll get to see that. Okay, I'm going to apply a force at this 60-degree angle. Okay, so the angle at that 60 degrees should be located where on this particular diagram? Where should my 60-degree angle be? Here? Here, here, or here? The top, right? The angle, the theta angle that we're talking about is between the radius, which our radius is right here, and the force that's applied, and this is my force. Okay? So this angle right here is 60 degrees. It tells us that in the problem. Okay? So it says we apply a force at a 60-degree angle to this wrench. What this right here is, if I can make it a perfect right triangle, this right here is that lever arm. It's the perpendicular distance from the axis point to where the force is being applied. So to find that lever arm, I'm going to draw a new kind of line here from my axis point to my force until I make a perpendicular or a right angle. Okay, and this would be called the lever arm. Okay? So what we're solving for here is how long is the lever arm and how much force do we have to exert. Okay, so to find the length of the lever arm, we know this radius right here is 0.25 meters. So to find the length of that lever arm, we're going to take r times sine of theta. So L equals r sine theta. So L equals 0.25 times sine of 60. Right? Because here's our 60-degree angle. This 0.25, this radius would then be our hypotenuse, and this L would be the opposite or the adjacent side. L is opposite or adjacent to our 60-degree angle? Opposite. So that's why we're using sine. Okay, do we see how those fit together? L equals r, which is our hypotenuse and our radius, times sine of theta, because sine is going to be our opposite side. So what is our L equal to? 0.21. And what's our units? What would our units be? If it's a distance. Meters, right? Because we're taking a distance of our radius times our angle. So that would leave us with a meter unit. Okay? Does that match what our book says? Pretty close, okay? The book says 0.22, so that's just a rounding.
That's what
Okay.
Yes, sir.
Okay.
Didn't round properly.
Okay. So now let's solve for the amount of force that we have to apply. All right, we know that torque is going to have to be equal to 35. We know this radius, or we know the lever arm itself. So if we solve torque equals FR sine theta, we're going to plug in 35 equals force times 0.25 times sine of 60. Okay. And we know that this term right here, we already know what that's equal to, so you could plug that in by itself if you wanted to. Doesn't make a difference.
That's quite a bit of force.
It's a pretty big force. Okay, so what do we get?
Yeah. 159.0.
159.1. Okay. Yeah, that's pretty close to what I got. I got about 161. Okay, just depending on if you leave your numbers in your calculator or not. Did you? Yeah. Problem. So we're going to keep in mind this same exact problem. What force would we need if we wanted to apply this force at a right angle instead of at a 60-degree angle? Okay, so if our diagram looks like this, we have our wrench. Mm-hmm.
So 35.
And we're applying a force of right here this time.
Right.
Yeah, do we even have a lever arm this time? No, because it would just be the radius. So we're going to solve 35 equals F times R sine theta. So we're still going to have to take 0.25 times sine of 90. Okay. So that gives us 35 equals 0.25 F. Okay. So that means our force is going to be equal to about 140 newtons. So that requires less force if we're going to apply it at a 90-degree angle. Okay? Okay, calculate the torque produced by a 75 Newton perpendicular force at the end of a 0.15 meter long wrench. Okay, if we say the force is perpendicular, at what angle is it coming in at?
60.
If something's perpendicular, yeah, 90. Okay, so here's our wrench again. If we have a we have a force coming in at a perpendicular to that wrench, that means it's coming in with a 90-degree angle.
Oh, I just
Okay. So here's our radius right here. All right, if we're going to take torque equals FR sine theta, our force we said applied was 75 newtons. We want our forces to be in newtons, so we don't have to convert anything. We had our radius in meters, which means we don't need to convert that. Sine of 90 we know is 1. So we're going to take 75 times 0.15, and we get what for our torque? 11.25. And what's our units for torque? Newton meters. Okay, Newton meters. So it says calculate the torque produced by the same force when we extend the radius of the wrench to 0.5 meters instead of 0.15 meters. Okay, do you think the torque will increase or decrease? Increase. So let's do the math and see if it works out.
37.5.
Okay, so here we're going to take torque equals 75 times 0.5 times sine of 90, which should just be half of 75. So torque is 37.5 Newton meters. And this is an increase from our last problem, right? The torque increased as we moved our radius out, or as we extended that wrench. Okay? Does that make sense? Kind of common sense, logically? Okay. I don't know why I have that number there. Okay. Go ahead and do this one on your own. Let's try and find an angle here. So this is going to require you to do a little bit more trigonometry at the end. Okay, so we have a wrench that's 2.34 meters long, or I'm sorry, 0.234 meters long, which would be our radius. We need 32.4 newton meters of torque, and we can exert this force. We're going to try and find this angle that we can exert the force at. Okay, so that means we're going to need to solve for that sine theta, and then we'll look for theta after that. Okay, so here was our torque equation. We're going to solve for theta here. To solve for theta itself, we need to take second sine. And if our calculator's in degrees, we're going to get 36.6 degrees. Do we all agree? Okay. All right, now let's look at net torque. What do we mean when we say net of anything? We've talked about net force before. What's that mean? Yeah, total or overall, right? Net force was our total overall left minus right, up minus down type force. Okay, so net torque is going to be the same thing. We're looking at a system of something. Okay, if this system is balanced, if something's not spinning one way or the other, okay, if it's sitting kind of at rest, and you can think of kind of a seesaw here or a teeter-totter, right? If that system is balanced, there's got to be an even amount of torque on either side. And they're going to have opposite directions of each other, okay? So our net torque would be equal to 0 if something is balanced, okay? Here's what this would look like. If we have a balanced system, something's at rest, it's not spinning or kind of sliding one way or the other, we have balanced net torque. So torque on one side is equal to torque on the other side. So T1 equals T2. If you arrange that to show that net torque equals 0, it would be T1 minus T2. And if you plug in our force times radius, and it would be sine theta if you need to, but most of these net force equations are just with no angles, really. We're just looking at a system here. So force times radius of the first minus force times radius of the second would give us a 0 net torque. So go ahead and turn to page 204. Flip one more page ahead, and we're going to look at example problem number 2. What this is telling us is that Carrie Ann, who weighs 56 kilograms, and Aisha, who weighs 43 kilograms, want to balance on a seesaw that's 1.75 meters long. Where should they place the pivot point? So they have different masses, so that means they can't just place it right in the center. They've got to place this pivot point somewhere different. So we're going to try and figure out what that radius would be for each of them from the pivot point. Okay? So first we're going to go ahead and solve for our unknowns, and we're going to look at the two forces. Okay? If we know that something is balanced, we know that it's going to be torque on the first side equals torque on the second side, right? Which means force of, I think in the book they're calling A and K. I'm just going to say 1 and 2. So force times radius of the first equals force times radius of the second. Okay, that's what we're looking for here, is that these are going to equal each other. Okay, if they're just sitting and balancing, the only force they would have acting on them is gravity, right? All we're looking for is F sub g would be the only force that's acting on them. If they're just balancing, they're just sitting there, right? We're gonna take mass times gravity for each of those two. Okay, does that part make sense? Okay. So they went ahead and solved for this for each of the girls individually. Okay, so F sub 1 will be our first girl, our 56 kilogram girl. So F sub 1 is going to equal 56 kilograms times 9.8, which would be what value? 548.8. Okay, and what about F sub 2? We're going to take our 43 kilogram girl times 9.8, and we get what? 421.4, and these are both forces, so they're in newtons. Okay, so all we've done right now is just solve for the force that's acting on each of them. Now we're going to start looking at the radius that each of them needs to be from that pivot point in order for us to get an exact balance. Okay, so what they're going to do here, if you look down at example problem 2, about halfway down, it says, define Carrie-Anne's distance in terms of length of the seesaw and Aisha's distance. So they're going to take R sub 1 basically is going to equal 1.75 minus R sub 2. Okay, because on that seesaw, she's sitting the leftover distance away from that entire thing. Okay, so we'll go ahead and say R sub 1 equals 1.75 minus R sub 2. Okay, do we see where that comes from? Yes or no? Okay, R sub 1 or R sub k in your book is sitting a certain distance from the pivot point, which means R sub 2 has to be the rest of that distance. We know the entire seesaw is 1.75 meters long. So if her radius, let's say, is 1 meter, that means this radius has to be 0.75 meters. Okay, does that part make sense? All right, so let's go ahead and start solving for these here. We can do just a simple substitution for this here. We know R sub 1 is going to equal this value, so we can substitute that. Okay, you guys remember how to do substitution in algebra? Okay, so let's go ahead and start plugging in our equations here. F sub 1 times R sub 1 equals F sub 2 times R sub 2. Okay, so our F1 we know is 548.8 times R sub 1, which we know equals 1.75 minus R sub 2. Okay, that's where our substitution came in. Do we see that? Okay, then we're going to solve F sub 2 is 421.4 times just regular R sub 2. All right, so let's go ahead and solve for R sub 2 here. We need to distribute this 548 through that parentheses, so 548 times 1.75 minus 548.8 R2. I'm going to move this problem up to the top so I have a little bit more room. So that's going to give us 960.4 minus 548.8 R2 equals 421.4 R2. Do we agree so far? Okay, so now we're going to add that over. Which gives us 970.2 R2 equals 960.4. So then to solve for R2 by itself, what do we need to do this 970.2? Divide it over. So that gives us R2 of about 0.99 meters. Yeah or no? Do we agree? Okay, so now how do we solve for R sub 1? Yeah, we're going to plug it back into this equation right here. So we'll take 1.75 minus 0.99, and we get about 0.76 meters. Okay, so that pivot point for these two people is not right in the dead center. Okay, because they have different masses. If they had the exact same mass, then their radius would be placed right in the dead center. Okay, but they don't have identical masses. So it's going to shift the balance of this entire system a little bit from the center. Okay, and you see in your picture on problem 2 that it's not placed right in the middle. Okay, you can see it's shaded a little bit toward that R1 or RK side.